Hi everyone. This is an example of a titration style of problem of solution stoichiometry. These types of problems, they really stand out because they all follow the same general format. Hey, someone went and did a titration experiment. Here's their data. Answer the problem. As soon as we see a big data table like that, which is the only style of question that has a data table like this for us, wow, it stands out. Oh, it's a titration style of solution stoichiometry problem. We're going to still follow our same 4 steps, which starts with balance the equation. Here the interpretation is much more involved than our other steps. We tend not to have a sentence describing what's going on. Instead, what we need to focus on is the title of the table. It's the titration of 25.0 milliliters of Na2CO3, that's sodium carbonate, with 0.352 moles per liter hydrochloric acid, HCl. We need to really focus in. It's the title of the table that's going to describe to us what the reaction is. It's Na2CO3 with HCl. So we need to come up with the balanced chemical equation. We have Na2CO3, sodium carbonate, reacting with hydrochloric acid. This is a double replacement reaction. The sodium and the hydrogen switching spots. The hydrogen 1 plus, CO3 2 minus. And the sodium 1 plus, the chlorine 1 minus. And we balance the equation like so. Now we have, forgot that too. We have 2 sodiums on either side, 1 carbonate on either side, 2 hydrogens and 2 chlorines. We came up with that balanced equation. That's always our first step. One more time, we had to pull the information out of the title of the table. We continue with our interpretation. What is the concentration of the sodium carbonate solution? Here's the sodium carbonate. What's the concentration? We're not surprised to see that. By definition, a titration is about solving for an unknown concentration. Now, the titration of 25.0 milliliters of Na2CO3. Oh, that's the volume. The volume there is 25.0 milliliters. Wherever the question mark is, that's R. If we look in the title of the table, we also have 0.352 moles per liter HCl. That's the concentration of the HCl, 0.352 moles per liter. The data table itself shows us that 4 trials were done. We had the final reading of the burette, the initial reading of the burette, and the volume added. If we notice, if we did 16.5, subtract 0.6, we have 15.9. So that's already set up. We don't actually care about the initial or the final reading. What matters to us is the volume of hydrochloric acid added. That's the only line of this table that has any meaning for us. We see that there are 4 trials. This volume right here, that we're going to use the volume of hydrochloric acid added. It's going to be the average of what we say 3 good trials. The first trial is off. 15.9 for the first trial. The other 3, 15.3, 15.2, 15.2. As soon as we see 4 trials that were completed, automatically we're going to omit that first trial. That's for every time. If you see 4 trials that were completed, ignore the first trial. It's never going to be the second or the third trial, always the first trial. It's going to be out of line with the others. It's going to be too high. So this volume is going to be the average of the 3 good trials, which is 15.3, plus 15.2 plus 15.2. Add the three trials together and divide by 3. We can take our time. We can do that math on our calculator. Maybe you can do it in your head. 15.3 plus 15.2 plus 15.2 divided by 3. That is 15.23333. Repeating, try not to round that off, milliliters. So, we took our time. We had to balance the equation and interpret the question, our standard first step. However, instead of having a sentence to pull the information out for balancing the equation, the chemicals in the reaction were described in the title of the table. Some of the values, the unknown was in the problem. Other things we also pulled out of the title of the table. The table itself, it's the volume added that matters to us. We had to omit the first trial and average the other 3 to come up with this value. If we end up with a repeating decimal like we do here, try not to round it off. Keep it on your calculator or find a way to use the unrounded value in your calculation. We move on. Find moles. Remember that titration, all of the extra work is on the front end. All of the interpretation is where the extra work comes. The math itself is always going to be C times V times R over G divided by V. That's always the same. So here we go. C times V of R, no. The concentration is 0.352 moles per liter. The volume is our average here, converted into liters. That's 0.01523333, etc. That's liters. It's still sitting on my calculator screen. And we're going to multiply by our next step, R over G. R over G, R over here, 1 over these given values, 2. 1 over 2. That represents red N, which now we're going to divide by the volume. Divide by the volume, these 25 milliliters converted into liters. 0.0250 liters. I still have this number on my calculator screen with the unrounded version. What I'm going to do right now is divide it by 1,000. Divided by 1,000. I took my average, divided by 1,000. So now I have this unrounded value on my calculator, which I can multiply by 0.352. Now I can multiply by R over G and divide by 0.025, 0.025. And I end up with 0.107242667. When I look back at all of the values that I used, I had 3 significant digits, so I round this off appropriately. 0.107. And this is the concentration that we found. Moles per liter. When we see a data table like this, that's an absolute guaranteed signal that we have a titration style of solution stoichiometry problem. There's some extra things to pay attention to with the interpretation, especially this idea that if there's 4 trials, omit the first trial and find the average of the 3 good trials. The stoichiometry calculation itself is always the same, C times V times R over G divided by V, to give us the unknown concentration that we were looking for. As always, watch those significant digits and units, and I hope that helps.